Hello, in this video we're going to talk about ramjets and scramjets, or what they're called, supersonic ramjets. So they're very simple engines that rely on the movement of the movement of the plane, the movement of the engine through the air to compress the airflow as it comes into the engine. So the thing with ramjets is that they can't produce any thrust when it's not flying through the air. Okay, so it needs some type of forward movement before it can start creating thrust. The air needs to be moving through the engine for the engine to work properly, but it can't force the air through the engine on its own, unlike a turbofan or a turbojet engine, where it has a set of turbines and fans and compressors that can suck the air in to the engine and then produce thrust. Okay, so this has nothing, can't suck the air into the engine all on its own. It needs to be flying through the air to begin with. Therefore, for the use of a ramjet, these are most commonly would be on like a missile or something where it can use a rocket engine, so like a solid propellant rocket engine or a liquid propellant rocket engine, to create the thrust to start, and then can kick over to a ramjet to kind of extend the range, and then to use ultimately less fuel than just a strict rocket would. Okay, so basically how it works is that this it's kind of like the cross section of a ramjet here. So we have this spike up here in the front, and then what this does is that as it's flying through the air at a Mach number greater than 1, so faster than the speed of sound, this compresses the air. Okay, so as it compresses, increases temperature and increases temperature. So this right here would be state 1 as we are looking at our diagram right here. So then we have a diffuser here where it kind of releases the pressure a little bit, and then this would be state 2. And then after the diffuser section right here, this is where fuel is mixed with the air, with fuel injection mixes with the air to state, and then meets with the flame holder, which is basically where the flame is in the engine. But the way the kind of flame holder works is that it's the flame or the spark or whatever it is lighting the fuel air mixture is kind of behind a wall, therefore creates an eddy, and so kind of mixes the fuel in the air more, gets a better lighting action. Because if like the flame was just sitting out in the middle here, the air is and fuel is moving so fast it might not light properly. You have the flame holder. So then state 3, which would be like right here after the flame holder, now into the combustion chamber. So you can see that, sorry. Into the combustion chamber. This is where the fuel and air light up, and then goes to state 4, which would be about here, and then goes to the nozzle, so where then the speed reduces, or it increases now here because it lit, so it chokes through this throat right here as a Mach number of 1, and then as it expels through the exhaust, the Mach number increases as it kind of expands to atmospheric pressure. And if you want to see the derivation for this, you can look at one of my previous videos where I derive kind of the Mach number relationship for a nozzle. So these are all states right here: airflow in, compressing, diffuser, flame holder, combustion chamber, nozzle, and then out the back of the engine. Here would be state 6, or this is the exit, would be out here. So your temperature max would be at this stage right here at stage 4. So this is your max temperature. Therefore, whatever material you're building the engine out of, it needs to withstand this temperature, because this is where it'll be the hottest. So review that one more time. Air is flowing, or the engine is flowing into the air. The air comes in at a speed greater than 1 when the Mach number is greater than 1. Comes in, gets compressed by the spike. Temperature increases, pressure increases. The speed decreases through the compression, kind of expands back. Temperature stays the same, pressure decreases. It gets mixed with the fuel, gets lit on fire, then it accelerates back out the nozzle, gets much hotter, hottest point right here, and then goes out the back of the nozzle. So with ramjets, they're most efficient at about a Mach number of 3, and then they can operate all the way up to, about Mach 6. Okay, they're most efficient about Mach 3. As you get down to Mach numbers, the efficiency lowers again, and then under kind of a Mach number of 1, they don't work as well. So the difference between a ramjet and a scramjet is that a ramjet, after the air is compressed, the Mach number is now less than 1. For a scramjet, which is a supersonic ramjet, the airflow stays supersonic the entire time. Okay, so now we're going to do a problem, and we're going to give it a couple conditions. For this, we're going to also do a non-ideal ramjet. We're going to give a couple of atmospheric conditions, a couple efficiencies, a couple pressure relationships, and we're going to calculate the pressure and temperature, kind of all of these points. And doing so, we're going to be able to calculate the exit Mach number, the impulse or the specific thrust, this thrust specific fuel consumption, the thermal efficiency, the propulsive efficiency, and the overall efficiency. All right, so we'll jump right into that. All right, so here are our conditions. We have a Mach number of 3. The atmospheric temperature is 216.66 Kelvin. The atmospheric pressure is 7,565.2 pascals. Our ratio of specific heats for our cold temperatures and our hot temperatures are 1.4 and then 1.3. We'll get into cold versus hot in a second. Our gas constant is 287 joules per kilogram. Efficiency of our nozzle is 0.98. The efficiency of our diffuser is 0.70. And our efficiency of the burner is 0.98. The pressure drop of the burner is 0.95. The temperature relationship between state 4 and the atmospheric temperature is 8. And our heat of combustion is 42 megajoules per kilogram. All right, so so cold versus hot, and we'll as we go through this. Okay, so as the air comes through here, basically all the states before the combustion chamber are all what we would call cold gas or cold, and then everything after, like through the nozzle, this will be hot gas over here. So you'll see that come up a lot of times. Sometimes if you're doing an ideal problem, you use the same values, but we're going to use different values for our specific heat ratios for cold and hot. All right, so we'll start with our inlet states. So 2 here. So what do we expect happen? Temperature increases, pressure increases. So our equation for temperature, so TO1, so this is like the stagnation temperature or total temperature at state 1, equals TA times 1 plus gamma C minus 1 divided by 2 times the Mach number squared. Okay, so take the temperature of the atmospheric times then this value using the cold gas value, because it's cold still, hasn't been lit, and then the Mach number, and then this, and we have all those values, don't need to solve for anything, and we get 606.65 Kelvin. That makes sense. The temperature when we compress the air is going to increase. And I also apologize if any of these calculations, any of these numbers are wrong, I do apologize. But they should be in the right ballpark. So now we'll find the pressure. So ignition pressure at that point would be PA times TO1 divided by TA 2 gamma C divided by gamma C minus 1. So raised to this value right here. And this would equal, and we have all these values, 270, what did I write down? 77,893.6 pascals. It should be 893, not 896. 893.6 pascals. Now, does that make sense? Obviously, getting compressed, pressure is going to increase. All right, so now we're in the diffuser states. So inlet states, we got A to 1. Now we got the diffuser, which would be about 1 to 2. Okay, and we could say that the temperature at the diffuser and the diffuser is about the same as the temperature at state 1. There's not a significant temperature decrease between that. But what there is going to be is a pressure decrease. So we need to find, so the pressure equals, at 2, equals pi d times PO1. So pi d will be the pressure drop between PO2 and PO1. And we expect pi d to be less than 1 because we expect the pressure is going to drop between states 1 and 2, which would make sense. So that pi d for supersonic flow is this equation right here. So this is kind of, I would call this like the supersonic part of this equation. And then the rest of this would be the same if it was a subsonic flow. So this is the equation for supersonic flow to find the pressure drop, and this would be so a pretty significant pressure drop between states 1 and 2. All right, so calculate that. So PO2 equals pi d PO1. Plugging into the numbers, we have all that. It'd be 94,155.4. I'm not plugging in all the values just to save time, but we have all the values. So yeah, so our nozzle or our diffuser efficiency, we have that. That is 0.7. All right, so now we're at the burner states. So this is kind of at the end of the combustion chamber. Okay, so we have TO4, that equals our temperature ratio times the temperature at A, which would equal 1733.28 Kelvin. Now this would be our maximum temperature. So the metal that we use to make, or whatever materials we use to make this, to make the engine, has to be able to withstand that temperature. And then we can find our pressure at state 4, which would be pi b times PO3. And we are going to say that PO3 equals PO2. So we're saying that there's not a significant pressure difference between states 2 and state 3, which makes sense. So we can call PO2 and PO3 equal to each other. Write that down. And then pi b, we are given that, and that is 0.95 for this equation. And that would equal 89447.63 pascals. All right, so now we have our nozzle states. And then we got, so temperature exit equals T6. That equals TO4, 1 minus the efficiency of the nozzle, 1 minus PA divided by PO4, and then we're going to use gamma E minus 1 divided by gamma E for this one. So the gamma E equals gamma H. So now we're at the hot gas values. Because we are back here, the gas is now, the air fuel mixture is now lit. And obviously a lot hotter now. Now we're using the hot value. And now we're going to find the temperature at the exit. And now we expect that temperature to drop as it is expanded through. So we have all the values for these. Temperature of our efficiency of our nozzle, 0.98. And we are left with 995.25 Kelvin. All right, moving on. So now we are going to find these values. So CPH, CPC. So these are specific heats. Yes, I think that's what they're called. So that would be for our hot gas, we gamma H R divided by gamma H minus 1. And then this would equal, we have all these values, 1,243.7 joules per kilogram Kelvin, which also equals our specific heat exit. And this equals gamma CR divided by gamma C minus 1, that equals 4.5 joules per kilogram Kelvin. So we need these values to find our exit velocity, which would be VE, so VE6 equals the square root of 2CP, the exit, times TO4 minus T6. Okay, we have all these values. CPE equals 1243.7, and our T6 is 995.2 Kelvin, 25 Kelvin. Oh, there we go. Plugging in our numbers here, we get 13,554.8899 meters per second. Okay, so now we want to find our Mach number at our exit, which would be VE divided by AE, VE divided by square root of gamma E RTE. So this again would be our 1.3, because it's the exit, it's the hot. Plugging in the numbers, we got 2.223. As you can see, the speed of the air coming out of the back of the engine has a lower Mach number than the air going in. But as we'll calculate right now, the speed of the air, so calculate VA equals MA times AA, 3.0 times the square root of gamma cold, R times TA. Now this will equal 885.15 meters per second. So as you can see, the velocity of the air coming out of the back of the engine is faster than the air going in, but the Mach number at the exit is less than the air going in. Pretty interesting. For an ideal ramjet, the Mach number at the exit will equal the Mach number at the entrance. So how about that? So with these values, okay, so last thing we need to find is our fuel ratio, fuel to air ratio, or yeah, fuel to air ratio, which would be CPH TO4 minus CPC TO3 divided by burner efficiency times delta HC, heat of combustion, minus CPH TO4. Now we don't have TO3, but we can say TO3 equals TO2 because there's not a significant temperature, there's no temperature difference between states 2 and state 3. Because state 3 is like right before it gets lit, So there's no temperature difference and no pressure difference between those. So TO3 equals TO2. Write that down. So our fuel to air ratio is 0.0396. We have all these numbers. Our delta HC is 42 megajoules, so you'd want to write that as 42 times 10 to the 6 joules per kilogram. And we have everything else. Now we can calculate impulse, which equals VE, so the velocity at the exit, 1 plus fuel minus VA, fuel to air ratio. Plugging in those numbers, we get 523.4. Really, the units could be written as meters per second, but that doesn't tell you much. You would really want to write that as 523.4 Newton seconds per kilograms. That tells you more about kind of the thrust, that value of kind of a thrust relationship that the impulse is created. Now we can find thrust specific fuel consumption, which equals the fuel to air ratio divided by the impulse, which would be 7.566 times 10 to the negative fifth kilograms per Newton second. You can also write this as kilograms per kilonewtons per hour, but we're going to leave it as kilograms per Newton seconds. All right, so now we have we have found the exit Mach number, we have found the impulse, thrust specific fuel consumption. Now we're just left to find with the thermal efficiency and the propulsive efficiency. But first, we're going to find the value of R, which equals VA divided by VE. So that equals, we have all these values, 0.6533. So now we are going to find our propulsive or thermal efficiency with this equation. And then, so this equals 0.505. And then our propulsive efficiency, this equation, that equals 0.8237. So these are very efficient. This will be a very efficient ramjet. That's our overall efficiency, thermal times propulsive, and that can equal 0.4156. So pretty efficient for a ramjet. Ramjets are very inefficient engines. They use a lot of fuel. They're not the most efficient, but they're really the only engines that can operate at, you know, huge speeds, very fast speeds. Okay, so I think that's about it. I think the last thing I want to say, I don't know if I mentioned this earlier, but kind of the efficiency of a ramjet decreases as you get in really fast temperatures, because the temperature difference between the inlet states and then the outlet states decreases. So you can't extract as much thrust or energy when the difference in pressures or difference in temperatures isn't larger. You want a large difference in temperatures. So there you go. We calculated temperature and pressures at all the states, calculated a bunch of good values to know to compare different engine specifications, and we learned what a ramjet is. There you go. Thanks for watching, if you made it this far.